In 1850, James Clerk Maxwell wrote a letter to one of his students and describes the ways that you can learn something. He mentions three important things. He told his student that you can learn with your heart, with your head, or with your fingers. And what he meant by fingers is the fact that you can learn something by working hard, study a lot, practicing, practicing a lot of problems, and be hopeful that you can pass a test. But the issue with this type of learning is that it takes a long time and it's not really good because you might forget a lot of things and you might not be even that creative regarding many things. The other way is by learning with your head. And what he meant by head is this idea that you think about something as deep as you can and as long as you can and hope to crack it. And this type of problem solving and innovation is very difficult because not everybody is able to do it. And it might take a long time. Exactly what Newton described was also like this, that he thought about stuff non-stop for even decades to crack them. And in the end, James Clerk Maxwell mentions another thing. He mentions that you can learn something with your heart. And by heart, he means intuition. And Maxwell himself definitely was one of the greatest intuitionists of all time in physics. In this video, I'm going to talk about Einstein and how he able to beat some of the greatest mathematicians ever, including Lorentz, Poincaré, and Hilbert, to the discovery of general relativity, special relativity, and the way that his philosophy practically went against everybody else in that time, but it was correct and it was proved, and in the end, it was accepted. This is a very interesting story, and I think it's going to put a lot of confusion aside regarding why we cannot say many things about gravity and why this is a correct theory. And even if you go to some of the university's philosophy departments, I've seen this firsthand. There are a lot of people who do not understand why Einstein's discovery and his philosophy in general relativity specifically was so different and so unique at the time, and even now. Like, if you read the history of science and physics, I don't think there is anybody else that can be totally separate from his time of the scientist and how they thought and eventually be proven to be right. It's a very interesting story. So for this start, let's just take a look at how the relativity story starts in the first place. Relativity starts with a very simple question. If you and I are both moving relative to each other, do we experience different laws of physics? Newton and Galileo concluded that no, we do not. But they also believed in absolute time and absolute space. So Maxwell himself was a bit suspicious of ether. And it is very interesting because he really never questioned it much, but there are records and handwritten notes that shows that he was thinking about some problems. And he never really published them as well because his theory was working perfectly and got totally accepted. But in some philosophical aspect, he was questioning the existence of ether. And then in 1885 came the famous experiment of Michelson-Morley, which is the real proof that there is no ether. But what is not being mentioned is that Michelson-Morley themselves never said that there is no ether. When they did their test multiple times, they actually started to look for other alternative solutions. They published like 3 papers on this. And the idea was that they were saying that if we cannot detect ether, then probably there is something wrong with our devices. There are some local anomalies. And they also came up with the term ether dragging, and they were thinking some mathematical aspects of the problem that maybe there is some dragging happening or something like that. And this was making a lot of paradoxes in physics because before that, the whole mechanical ideas of physics and Newtonian mechanics was very successful. There was nothing wrong with it. And nobody could just say that there is no ether, because if you just say that, you are discarding thousands and thousands of years of experiment that's been done, and they were done perfectly amazingly great, and Newtonian mechanics was working 100% correct. So there was nothing wrong with it. And they didn't want to just say that there is no ether. And they started to look for other problems and other solutions. And one of the most interesting paradoxes there was the idea of star aberration and the whole concept that if planet Earth is locally dragging ether with itself, then we shouldn't measure what we measure. And they tried to solve this mathematically, but they couldn't really solve it because what they were measuring was different from what they were theoretically measuring, and they were saying that there is something wrong here but we cannot really solve it, and this is because we cannot detect ether, and that was the problem. And then came the famous Lorentz and Fitzgerald contraction, and they literally saved ether for a few years. And what they said was that if you go against ether wind, the electromagnetic forces of the object that are experiencing, when they go through ether, especially against ether wind, they are being shrunken and compressed. And that tiny compress and tiny shrinkage is why our devices cannot detect ether. So this was the solution that came from Lorentz and got accepted very fast by everybody because there was no need to discard ether. It was just some philosophical idea that he actually showed mathematically as well. And that factor, interesting and very famous factor of the square root of 1 minus v over c to the power of 2. So that was the factor of the shrinkage that we see in a Lenz contraction. And he said that, yeah, this is the reason, and that's why we cannot detect ether. But in 1905, this paper by Einstein came from nowhere. Nobody knew him. And he just said that there is no ether, and what happens if time and space are relative. This was a completely different point of view. So what was different about this was that, first of all, Einstein totally discarded this idea of absolute space in a point and said that there is no ether at all. There is nothing wrong with our measurements, and there is no need for all of these philosophical ideas. The point is that there is no ether, but time and space are relative to each other. And this is a very interesting point of the story because this is where Poincaré comes in and tries to actually save ether, but in the end he fails because he doesn't really have the intuition that Einstein has regarding this part of physics especially, and why there mustn't be any ether at all, and you can just go through physics and do a lot of discoveries without any need for ether. By 1895, Poincaré was totally involved in physics, and he was aware of the Michelson-Morley experiment and all the paradoxes that it was causing. So he wrote a paper, and in that paper, he actually coined the term relativity years before Einstein, and also the time dilation parts of the Lorentz transformation is actually mostly done by Poincaré. And he also fixed a few mathematical conventions and problem in Lorentz transformation. And what we have as Lorentz transformations in textbooks right now is mostly done by Poincaré. So he fixed a lot of mathematical issues. And he also understood this problem that if you have two observers, one has a constant speed and the other one is at rest, they can never actually detect the absolute speed. And because of this, it is impossible, it is physically impossible for any observer to detect ether. So Poincaré understood that perfectly. But what makes that different from what his view was compared to Einstein was that Poincaré was looking at the problem as a totally theoretical mathematical idea. And he was saying that ether exists, we have time dilation and we have Lenz contraction, and the speed of light appears to be constant. So he was just saying that ether is just a mathematical convention and a mathematical tool, and we can do measurements and we can do physics with it, so don't bother anymore. Just accept that it is and move on. But Einstein didn't believe in that. He was just saying that it is impossible to accept ether because we cannot detect it at all and it should be measured. And this part of Einstein's philosophy is what caused him yet later in life, like decades later, to have some problems with aspects of quantum physics because he already proved, like 40 years before, that you can actually do fundamental solutions and gives fundamental solutions in physics by believing in this philosophy. So it is a very interesting time that Poincare is saying that ether does exist, but we cannot measure it, so just move on. And Einstein is saying that, oh no, ether does not exist and we cannot move on. We have to fix this problem totally and philosophically as well. So let's just take a look at the difference between their view and see what we can get from it. Now let's take a look at the difference between Poincare and Einstein's philosophy on the subject of ether. So what Poincare was saying that you do have absolute time. So there is an ether out there. There is a real truth out there that you can never actually find out. And if you want to sync two clocks together, using, for example, a light signal, you will find a bit of error. And this small error is so tiny and minute that you can just ignore it and use your local time. So he was saying that yes, the absolute and true time is actually, for example, 12 o'clock, and what you measure is a bit different. But the difference is not very important. Just use this different, accept it, and say that this is a convention that we have. It's a mathematical tool that we use, and we have to use it to fix our approximations and get a better result, and just move on and say that this is correct. So this was his philosophy, and interestingly it was the philosophy of most of the physicists back then. And then came Einstein and he had a totally different worldview on this. He was saying that if you have two observers and you want to sync the clock together, it is almost impossible because this discrepancy between two clocks are actually both real for each observer separately. So he was saying that there is no error, there is no hidden ether, and the clock and the time that observer A is actually witnessing is correct for himself, and the ones that observer B or C are also witnessing are also true. So he was saying that there is no absolute true time, there is no absolute true space, there is no absolute true reference. All of these are just totally relative to each other, and difference between them comes to the observers themselves. So this was a totally different worldview on this subject. And when you look at this, you might say that this doesn't look very different to me. Why this is such a big concept? But the problem is, if you study physics and if you want to develop your theory based on these two different concepts and philosophies, you will get to the very different points very quickly, especially in relativity, and that's the very important factor here. So you really cannot develop the same theory with the different philosophies, and this is the very interesting part of the story, why Einstein was very different than almost everybody else in the history of physics. So what is interesting is that mathematical wise, on the knowledge of mathematics, Poincare was much ahead from Einstein. They knew almost exactly the same thing about this concept in physics. Poincare had much more powerful mathematical understanding, yet he didn't really have this intuition on how to interpret this. He still believed in old philosophy and he still believed in ether. He just couldn't really accept the fact that if you don't have any ether, then there is no true time, there is no true space. So after 1905 and after Einstein published his papers, he knew that there was one more step to go through, and that was the idea of adding gravity to everything. But he also noticed that it's not an easy task to do because it was a totally different mathematics. And he really didn't knew about that type of math, and nobody knew. And that was the idea because there wasn't a lot of connection between physics and math in a way that we know it today. So he had to go through everything and find out what we can actually use to make something like general relativity practically. So it took him like 10 years to do that. And what is very interesting is that, for example, Lorentz died not believing in Einstein. Like they were not enemies or something. They were friends. They were talking a lot, posting a lot of like letters, discussing philosophical arguments and all those things. But for example, Lorentz never believed that there is no ether. He actually believed until the day he died that ether exists and there is something wrong with how Einstein's philosophy is working. But this was coming to the fact that he was raised in an academic environment that believed in ether, which was very conventional. Everybody literally believed in that. But when you look at the history, you see that even then, not everybody was like this. For example, one of the biggest criticizer of Newtonian absolute space and time was Mach, Ernest Mach. And it is very interesting because Einstein mentions like one paper in his paper in 1905, one person, and that person was his friend, who he had a lot of like a talks and arguments about philosophy and helped him a lot. He wasn't a mathematician, but both of them, Einstein and his friends, were really were fascinated by Mach, and they read a lot of Mach's paper. And Mach was one of the biggest major criticizer of the absolute time and absolute space. So you can see what was his mentality coming from. And Einstein like wrote about this all in his biography and even in papers and stuff. He was mentioning all of this. And by 1910, and even before that, even Poincaré started to believe that there is no ether. But he was just still saying that it's just a convention. I'm a mathematician. I'm not a physicist, so I really don't care about that, which is understandable. In 1914, Einstein gave like a few seminars here and there and started to give these seminars in University of Göttingen in Germany. And there was that the place that one of the greatest mathematicians of all time, David Hilbert, was also working. And when Hilbert was listening to Einstein, he found out quickly that what was Einstein trying to do was the greatest fundamental contribution to physics. So he knew it very quickly, found out about that. So in November 1915, both of them they were like in a very compressed time speed. Who can publish this first? And they were actually writing papers, like letters to each other as well at the same time, discussing this. But the issue for Einstein was that he didn't have much knowledge in differential geometry, and that was the biggest challenge he had like for the past 10 years. But David Hilbert was the master. He was one of the greatest mathematicians of all time. So Hilbert beat Einstein in publishing his paper by 5 days. So he published his paper showing that gravity is not a force in distance, it's actually mass manipulating space and time. And he showed that 5 days before Einstein, and he published the paper with the field equations in it. But he also retracted it, and later he said that any schoolboy in University of Göttingen knows about four-dimensional space and four-dimensional mathematics more than Einstein. But he managed to beat all of us mathematicians to it. And the credit of general relativity is totally for him, because none of us have the intuition as he had. And that is the most important factor, what makes him so different compared to anybody else in history. And I would say that I still don't think many people, even in higher levels of physics today, understand general relativity and the concept of relativity that well. It's a very complex idea, and even though the mathematics of it might get a bit easier after a while in general relativity, the concept of like a philosophical aspects of it will always be challenging and will always be very difficult to get. And that's why after like all these decades, you can still see a lot of theories coming out that is, like, for example, does ether exist even? Sometimes you can see it. There is a book, I'm going to mention all of this in the description. There is a book that lists all of the tests and experiments after Michelson-Morley that have been done to detect ether. They were being done even now in universities, but there is a lot of them. Like, there is more than 50 mentioned in that book. So we can just say that there is no ether. We cannot really measure it and we cannot really see it. And there is not just one test, there is like hundreds of tests that have been done. So we know about that. And another factor that is very interesting is that the gravity itself, even after general relativity, is still a very, very unknown entity. That's why you still see a lot of people talk about it, a lot of physicists still give new ideas about it. But it is also very important to consider that we only have one real theory of gravity after all these years, and it has been proven times and times. The simplest one is that, like, the GPS works just singularly, and the only reason GPS works is because general relativity is correct. And there are a lot of tests that's been done, not just by GPSs, like there is a lot of them, but there is so many evidence that just shows general relativity is correct that there is no way we can deny it, that there is no ether and there is no absolute time and absolute space, and general relativity specifically is correct, and Einstein's views on physics is correct. And that was the main purpose of this video I wanted to make, because I can sometimes, sadly, I see here and there that they say there is something wrong with these series and stuff. But the issue with that, and this is not just like a normal people. I actually heard this from a person who was studying philosophy of science back in universities when I was doing my master. And the issue with that is, my opinion is that these people really don't understand the philosophy and mathematics of the idea. So it's not just philosophy and it's not just mathematics. You need to know them both at the same time to really understand quantum physics and general relativity specifically. So it's not a single way that you can understand it. So I hope you like this video. Please let me know in the comments if I can add something or change something. Thank you for watching.